Thank you. Thanks a lot, Professor Noparat, for the invitation to this seminar. It's an honor to me and to deliver this presentation for this audience. And in my presentation, I'm going to focus on technology, especially AI, technology, automation, and optimization for sustainable forest operation. I think Lauri did a very good job to show the Finnish forest sector. I'm going to focus more on the global sort of forest sector, showing how these sort of new technologies are shaping forestry globally. Okay. By the way, this is my email, and I have 2 emails, so you can contact me if you have any question after the presentation. But as you said very quickly, I did my PhD in Oregon State University, my master and bachelor in Chile. I moved to Finland 3 years ago, 17 years in Australia, and this is new. I'm coming back to Australia in June this year, so I'm going to be very close to to Indonesia. So I'm going to be professor. That's the title, Industry Chair of System-Based Systems and AI Integration for Increased Timber Production at the University of Sunshine Coast. So I'm going to be working there from June this year. So. And this is the outline for my presentation. So I'm going to start talking about the global forest scenario and then why it's important to automate forest operations. I'm going to explain the concept of Industry 5.0, giving an overview of that concept. Then I'll move on to explain data analytics for improved decision-making. I'm going to talk about some work I've done with wood supply chain optimization. I'm going to present some emerging and disruptive technologies, the key drivers and barriers to adoption, Forestry 5.0 solution, and also takeaway messages. And now I remember, Noparat, you mentioned IUFRO. I was deputy coordinator for 7 years at the IUFRO, so it's good that IUFRO is sponsoring this seminar. So this is the global forest scenario. There is an increase in demand for wood, so it's a challenging one. You can see here the numbers. This is an exercise that I did with my major professor in Oregon like 20 years ago. So the numbers could be a bit outdated, but this is what our prediction 20 years ago. There will be 10 billion people by 2050. 68% of the people will be living in cities in 2050. The demand for wood projected at 6 billion cubic meters under current consumption rates. The current supply is only 3.5 billion cubic meters, so there is a significant gap in timber production. So that means we will need, dependency on the assumption, between 80 and 100 million hectares of new plantations needed to meet the future demand. So most of the timber to satisfy the demand will come from plantations. I know some people complain about plantation, but we have to acknowledge that they play a key role in satisfying the world demand for timber. So that means also that our harvesting capacity would increase 4 times over the current levels. And also, we are seeing some sort of trends. For example, now we are seeing more in some countries harvesting in marginal soil, in marginal terrain, and state terrain, and increasing thinning operations. Okay, so some things are changing. And so delivering the right product to the right customer on time and on specifications is becoming even more challenging. Okay, so the person who is driving that machine over there is actually making very important decisions. They have to be productive, efficient, reduce waste, and maintain the sustainability of the forest operation. And also, foresters they spend years, growing trees to create potential value in each stem. On the right, we have could be a beautiful rata pine forest in New Zealand. And so what is the challenge here? The challenge is to capture that value optimally, delivering the right product to the right customer on time and spec. But also, we need to do the harvesting in an environmentally and socially acceptable manner. So Lauri already did a good job explaining all the dimensions of sustainability. But that's our responsibility and our challenge. How we capture the value that we created for so many years. I'm not very familiar with the forest in Thailand, but at least in Australia, we grow sometimes forest for 40, 50 years, and that's the challenge, how we capture that value 50 years later. So what is the current state of Cactulan's operations? So you can see here, harvester and forwarder rely entirely on human operators. They're labor intensive, inconsistent sometimes, and environmentally challenging. And forest value is built over decades, must be partially lost at the harvest. That's why I said before, the job of that person driving that machine is very important. So basically, the benefits of automation are exactly the same benefits as when we introduced mechanization in the Nordic countries at the end of the 60s or early 70s. We want to improve, to be more efficient, boost our productivity and optimize material flow. We want to reduce the human exposure to hazardous environments, but also from a sustainability point of view, we want to lower fuel consumption, reduce soil compaction, and improve our biodiversity monitoring. In terms of mechanization, this is from Finland. So Professor Kalle Harha provided this slide to me. So basically, you can see here in Finland and in the Nordic in general, operations are fully mechanized. And that occurred, as you can see here, from around 2005. And now 100% of the operations in Finland are fully mechanized. Okay, this is in first thinning, other thinnings, and also regeneration fillings. And this is the situation of Cactulan's operations worldwide, globally. And you can see here that, of course, the Nordic countries are, a big proportion of the operations are Cactulan's operations. We don't have Thailand here, but we can see Malaysia. I don't know if the operations in Malaysia are similar to Thailand, but Malaysia is very at the border nearly, so not a lot of Cactulan operations. And then we had full tree and tree-length operations. So again, at the top, in South Africa, New Zealand, the United States, and Canada, they use mainly full tree and tree-length operations. And again, we see, Malaysia is also with some full tree and tree-length operations. Okay, but that's the situation globally about the share of Cactulans and full tree and tree-length operations. Now, Industry 5.0. So at the moment, we are living what is called Industry 5.0. But I would love to start with this figure because it shows how we have transitioned from the first industrial revolution in 1780 to the last one, 5.0. So you can see the first one was shaped by the use of machinery, water power, steam power. 120 years later, we had the second industrial revolution. So basically consisting of mass production, assembly lines, uses of electricity. Then only 7 years later, we have the third one, basically shaped by computer and automation. 30 years later, we have the fourth one, characterized by internet and cyber physical systems. And it took only 20 years to pass from the fourth to the fifth, okay, which is more now characterized by human cyber physical systems. That's the current industrial revolution that we are living at the moment. Okay, so the core principles of this Industry 5.0 or the fifth industrial revolution are human centricity. So humans collaborating with robots, not competing. So I'm getting the benefits from introducing robotics in the different production lines and systems. Resilience, so how we can use this sort of technology for make more flexible and more robust sort of production lines. And in the case of forestry harvesting systems, how we can use this technology to make more sustainable and systems, for example, with lower fuel consumption, with less waste, etc., and how we can customize solutions for different customers with different needs. And then you have some technological pillars of Industry 5.0. I'm not going to go in detail of all of those, but in forestry, I would say big data analytics, supply chain integration, now robotics, simulation, and augmented reality are basically becoming very, very popular in forestry, and also artificial intelligence. So I'm going to show a few examples of what we are doing with the use of those technology in forest operation in a moment. And this is the value chain. I took this figure from a project that I'm coordinating in Europe. It's called Opti4Value. So if you want to learn more about this project, go to that webpage, opti4value.eu. But basically, we mapped we map the forest value chain from forest inventory to wood processing, so you can see all the activities, the phases of this forest value chain. And here, the important thing is to recognize that we are making important decisions in all these stages, but we need to also understand or see that this is we have to see that the forest value chain as a system with complexities, with interdependence, with interconnected decisions. So we need to understand how different decisions at different points in this value chain are going to affect the other phases of the forest value chain. Okay, and in the middle again you have some technological pillars shaping or they are shaping the forest value chain at the moment. Data analytics is becoming very, very, very important. It's a key element. Here you can see that, well, basically, when we move to the left to the right, we are increasing our complexity in terms of what sort of analytics we are applying to solve the problem. On the y-axis, we have from the bottom to the top, we increase our competitive advantage, let's say. So you see here different types of analytics. On the left, you see descriptive analytics. So, for example, what happened? You have a machine working in the forest, and you want to know what happened with that machine. What was the productivity of that machine? But then you want to know more about that machine. For example, why that did happen? Why the machine had that productivity? So that's called diagnostic analytics. And then in the future, you want to predict what's going to be the new productivity for the machine working in a different condition, based on historical data. So that's basic predictive analytics. So we do a lot of this sort of analytics in forestry. We want to predict forest growth, we want to predict the productivity of forest machines, etc. But then we have what is called prescriptive analytics, and it's only here where we can optimize the system. So that's why we use optimization and to try to optimize course of action, how I can do the best with a system, with the machines, with a harvesting system, with the logistics, okay? What should I do to get the best results, okay? So this is more complex. Prescriptive analysis is more complex than the previous analytics. In the middle between predictive and prescriptive, we have now AI, for example. AI is a very good tool for doing predictions. So you can use methods like random forests, things like that, ECBoost, and different techniques to make better predictions and feed the optimization model with much better data now. So that's the good thing about the interaction between AI and optimization at the moment. And here, I'm going to move on to present some example of tools that I have developed in the past. So here we have 3 tools. So I'm presenting FastPlan. FastPlan is an annual tactical harvest planning tool. And so, for example, let's say you're a forest planner, and you need to determine when to harvest those coops in different colors. Let's say, for example, you had 5 years to cut those coops. How do you do that job? Okay, how do you optimize the cutting of those coops in a 5-year planning horizon? So once you know that, once you optimize the harvesting, you basically pass those solutions. Those solutions are going to be an input for the next tool, MCPlan. MCPlan is more like in a monthly operational scaling sort of harvesting planning tool. And here we can include, for example, moisture content management. Actually, many years ago, I worked in Finland with my colleagues from Luke, and trying to optimize drying time. At that time, they were drying biomass at the roadside. So the question was for how long we should dry this material before doing the transportation. Okay, so we developed a tool, BioPlan, and now that tool is called MCPlan. And another tool that I developed when I was in Australia was Fast Track. Imagine you are a transportation planner. You have 50, 100, 200 trucks that you need to route on a daily basis. And so you need to send those trucks to different coops, to different forests, and then to different mills, in an efficient way. So at the minimum cost and satisfying all the constraints. For example, truck drivers cannot drive for more than 10 or 12 hours. So it depends on, some mills are open only for a few hours. Other mills are open 24/7. So you need to satisfy a number of constraints and with those tools. And here we had more information about the different tools. So again, fast plan, we are maximizing net present value because we are optimizing the cutting of those forest cubes, but also we are optimizing forest roads when the roads should be built or improved to move the timber from the different cube to the different mills. So you see here, decision is when to harvest each stand or cube. And the solution technique, well, it's a quite advanced sort of meta-heuristics called threshold accepting. Yeah, this is the interface for MC plans. This is an Excel-based tool. And here we want to minimize total supply chain costs. The decisions are when to harvest, when to do the transport, and for how long to dry the wood in the forest. And the solution technique is linear and mixed integrated programming. And fast track, that's the interface. And we want to minimize costs or empty track distance. There are different metrics in transportations. Decisions is how we allocate the track to different transport tracks, and the solution techniques is simulated annealing, which is another meta-heuristics. And here, these a few examples of emerging and disruptive technology we're being testing and in some cases applying in our work, both in Australia and now in Finland also. We've been testing virtual reality tools, and you see example use augmented reality and virtual reality tool for training people in forest operations for doing virtual forest inventory and things like that. In the middle, you see a lady at the top, controlling a harvester with a joystick, so remotely controlled machines. So that's actually a commercial system I saw in New Zealand. In New Zealand, sometimes they have very steep terrain, very in a very unsafe conditions. So they are already working with remotely controlled machines. And on the right you have autonomous vehicles. But also a few weeks ago I went to Sweden to see a new system for tagging logs. This is a digital printing system. So the difference is that it could be located on a forwarder. So basically, when the operator grab the logs, he can tag the logs in the forwarder. Okay, and this is linked to this information could be added to the HPR files. So it's you know exactly where the log was tagged, so you know the location, and then you can identify different log when they arrive to the mill based on that information. And this is something also I did when I was in Australia. I was working with a company who was interested in drying logs at the roadside to reduce transport costs, but also they were interested in adopting technology for measuring solid volume of logging truck in a few minutes, in nearly 1 or 2 minutes. So you can see different technology, commercial technology at the top, so the top left. And LiDAR system, some system based on the stereoscopic cameras, and etc. But also before we, the company purchased those systems, I basically offer a different approach, a different solution. I said, let me fly a drone to see if I can get a 3D map of the logging trucks, and if I can do the same job. I was able to do the same job. Unfortunately, my system wasn't in real time. The company needed something in real time, very quick. Okay, but at the moment we're writing a paper with my PhD students, so we are now using deep learning to identify log from point cloud data, and as you can see on the right, and now in a few seconds we can identify the log and estimate solid volume and gross volume using deep learning and point cloud data. So we are moving quite well and quite fast in that field. And here, sensor technology and harvesting equipment. So now companies are using this sort of system for capturing data in real time to produce point cloud data and how to improve decisions in the forest, especially in the Nordic, decision related to thinning. Okay, so here there's a few examples with different systems developed in Sweden, in Finland and Sweden. Ponsse developed that system on the left. So basically, it's a LiDAR sensor that is scanning trees around 20 meters around the machines, and presenting, the location and of the tree to the operator. And in the end, with that information, he can determine which trees are going to be removed during the thinning. The Nordic Forest Automation Company developed a similar system, so the one in the middle. We've been doing the same with our own LiDAR system on the right. So we purchased the Kudan system, and we put the LiDAR sensor on the machine, and also we've been able to doing this kind of course, they are they are a bit behind the commercial system, but we've been trying to do something similar in our own research. But also we propose a second approach. Instead of doing, this is real time, and you can imagine doing the things in real time is quite challenging. You need to do the scanning, process the data. By the way, this system don't optimize. They just present information to the operator, but they don't optimize the tree selection. So we propose with something different. So we propose a system where you pre-scan the forest, you go to the office, you do the optimization, you determine which trees should be removed during the thinning, and then you optimize the thinning solution, and then you pass the solution to the operator. So then, the operator go to the forest with that optimal solution. So in the forest, you just put the solution on a screen, and he can see the optimal solution. Of course, we need system like this. We need to have system like this. Once you have a point cloud data, because you have to go to the forest a few days before the thinning operations, you need to do a good detection, a good description of the trees. So we are working also on developing systems like the one you see here, from point cloud data, using deep learning and other advanced systems, how we can identify single trees, okay? Because that's crucial for the solution we are proposing. And coming to the end of my presentation, this is just something that I did in my PhD more than 20 years ago. And it was, at the moment, we had only talked about external characteristics of the logs and the trees. But 20 years ago, the focus of my research was on how we could capture internal wood properties using different sensors. In my case, with near-infrared sensor. And most of the inspiration came from that machine that you see on the left, agricultural machine, collecting the grain when, from the crop. And then the blue box is a near-infrared system, so you get the spectral curve. And in the end, you can predict, protein content, moisture content, and oil content, for example. And because the machine can with a GPS, in the end, you can create maps based on your variable of interest. For example, protein map, or a moisture map, or an oil content map. In my case, it was going to be a wood density map, a harvester with a near-infrared sensor in the harvesting head, collecting that wood chips and getting the spectral curve with the near-infrared sensor. And in the end, I was able to predict wood density at different heights of the stem. So I was able also to optimize the backing of the stem using that information. So it was the same sort of concept, but the inspiration came from that machine. Yes, just to finish, what are the key drivers for adopting this sort of the fifth industrial revolution technologies? So we are facing labor shortages and aging forest workforce. There are rising operational costs, demand efficient gains. There are more stricter environmental regulation, consumer and supply chain sustainability requirements. There are a need for competitive advantage through data-driven decision and improved safety record and reduce workplace injuries. We haven't talked too much about barriers, because people from the industry, from the companies, always ask me, where are the barriers? And there are some barriers. Of course, this is not free. They want to implement some sort of these technologies. There is sometimes a high upfront investment. So in hardware and software, you need connectivity. Sometimes people don't like changes, so you need to really educate people to the changes. And sometimes there is a steep learning curve for operators and planners. There are some data quality and standardization challenges. That is not trivial. Sometimes people don't want to share data. That's another issue. They are resistant to change from traditional operators. As I said before, they don't like changes. They don't want to do something different. They've been working from the same way for 30, 40 years, and now you want to make a change. So that's challenging. And then the more technical issues with interoperability. So I think I'm gonna some takeaway messages. Basically, again, people from the industry always ask me what's going to be the first step if you want to implement. What I always say, just pick the low hanging fruit, something that could cause a big impact at the lower cost. Okay, but the first thing you have to do in any system is to start measuring your system. Collecting data. Because the first thing here, the first takeaway message, you cannot manage anything if you don't measure the system. Okay, so you want to improve a system, you need to collect data from that system. Okay, and then identify opportunity in the value chain, set clear goals, leverage data, engage people. That's very important. Think outside the box. That's very important. Open your mind outside the box. Automate where possible, optimize where necessary, and adapt continuously. And sustainability forestry is a continuous journey of innovation and collaboration. I think that's it. Thank you very much.